Okay, so we're not going to focus on volumes where you really have to work too hard to figure out what the area function is equal to. Instead, we're going to consider sort of a systematic family of solids, and these are called solids of revolution. And the idea here is this: we start out with a region in the plane, and we rotate it about the x-axis. Now, when we do this, we carve out a region in space. We carve out a solid, and it looks something along the lines of this. So our original region was right here. We rotated it around, and we got a whole sort of region swept out in space. The nice thing here is, since this entire region is made up out of rotating this thing, if we look at any cross-section, it's really the path that a line segment perpendicular to the x-axis makes as we rotate around the x-axis. And the path that it sweeps out is a circle. So all of our cross-sections here are going to be circles. And in particular, the height of each of these cross-sections, the radius rather, is going to be f of x, the value of the function. So that means that our area function is going to be the area of this circle, which is pi times the radius squared, and the radius is f of x. So we get pi times f of x squared. This means that the volume is going to be equal to the integral from a to b, because that's how our region is defined, pi f of x squared dx. Great, so it's a nice systematic sort of thing. And a quick note, we call this the disk method because our slices are all disks. They're all circular disks. So let's find the volume of the solid generated by rotating the region bounded by y equal to x equal to 1, and the x-axis about the x-axis. So our solid is this region right here. Great, there's the line y equal to x, going from 0 to 1. Fantastic. It's a triangle. It's a nice right triangle, and we revolve that around the x-axis, and what do we end up with is a cone. This is a right circular cone with height equal to 1, and radius is also equal to 1. But we don't need to really worry about any of the details here. It's all really figured out for us, because we know that the volume is going to be the integral from a to b of pi f of x squared dx. A and b are where our region begins and ends, so from 0 to 1, our function is given to us, it's x, so we get x squared dx. So we get pi x cubed over 3, integral of x squared is x cubed over 3 from 0 to 1. I plug in my limits, and we get pi times 1 cubed over 3 minus pi times 0 cubed over 3, which is just pi over 3. All right, now let's find the volume of the solid generated by rotating the region bounded y equal to the square root of 1 minus x squared, and the x-axis about the x-axis. So the square root of 1 minus x squared, that is the semicircle. Since we're looking at the semicircle of radius 1, since we're looking at the entire region bounded between this and the x-axis, it's this entire semicircle. When we rotate that about the x-axis, we end up with a sphere, the sphere of radius 1. Cool. So the volume here is going to be the integral from -1 to 1. It's the leftmost point, the rightmost point, of pi times the square root of 1 minus x squared squared dx. And when I square the square root, I get the integral from -1 to 1 of pi times 1 minus x squared dx. Cool. I can leave the pi there. The integral of 1 is x. The integral of x squared is x cubed over 3, and this goes from -1 to 1. I'll plug in. I get pi times 1 minus 1 cubed over 3 minus pi times -1 minus -1 cubed over 3. This gets us pi. 1 minus 1 cubed is 2/3. Minus pi times, this is -1 minus -1 over 3. So that's going to be -1 plus 1/3, which is going to be -2/3. So at the end of the day, we get 4 pi over 3. So that is the volume of a sphere. And you can compare that with the known formula that the volume of a sphere of radius r is 4 pi r cubed over 3. All right, here's question 2. Find the volume of the solid generated by rotating the region bounded by y equal to e to the x, the x-axis, x equal to 1, and x equal to 3 about the x-axis. And, you know, the numbers aren't going to work out super nice here, but yeah, sometimes they don't.